Hi everyone. In today's video, we will be covering Chapter 7, which revolves around the idea of estimation and confidence intervals. Up until this point in the semester, we've been primarily concerned with descriptive statistics. In the last two chapters with the normal distribution and sampling, we've started talking about this idea of inferential statistics. And today we're going to expand upon that conversation more by talking about the first of two ways that we can use sample data to estimate population parameters. So this is how we can make inferences about a population. So today we'll be covering this idea of confidence intervals, which tells us that the population parameter, such as a mean or a proportion, lies within a certain range of value. In the next lecture video, we will be covering hypothesis testing in both Chapter 8 and a little bit in Chapter 10, which covers inferential statistical tests that use sample data to evaluate the probability of a hypothesis about a population. But again, for the purposes of today's video, we're going to be focusing on this first technique, which is through confidence intervals. The first idea I want to revisit briefly before jumping into our conversation today is about sampling distributions. So recall that sampling distributions are the distribution of a statistics. And oftentimes we've been revolving around this conversation with means and proportions, and this would be for all sample outcomes. And so it allows us to link our sample to a broader population. And if we have a representative enough sample, we can extrapolate and infer outcomes about a broader population from our sample. We also assume that the shape is normal, so revisit our information from Chapter 5 about the normal distribution and also ideas about the central limit theorem. Its mean is the same as its population mean, so again, that central limit theorem idea once again. And lastly, its standard deviation or standard error is the population standard deviation. So again, just moving from that idea of the small n to the large n, and we'll get to that in just a second here as well. Before diving into the rest of our conversation with confidence intervals, I want to make sure that we have a firm understanding of the statistical notation that we will need to use. And in this case, this chart should look pretty familiar to us. So we have our mean, proportion, standard deviation, variance, and sample size notation. And we've seen this chart before in reference to these first two columns in terms of the sample statistic and population parameters. The last thing I want to make a note of is the notation for a sampling distribution. And so this looks pretty similar to what we use for a population parameter, except for the mean, we are using a little y bar as a subset to our mu. With proportions, we are now changing that to our population mu with a lowercase p to designate that as the proportion. And lastly, in terms of standard deviation, we are using sigma with a little y bar notation to designate the standard error of the mean. When we're talking about the standard error of a proportion, though, we will designate that with the sigma sign with a lowercase p. So just keep that in mind. You'll see that throughout the duration of this particular lecture, as well as both Chapter 8, 9, and 10, and later conversations that we'll be having about hypothesis testing and chi-square. So if you need to use this chart as a reference, please do so, but just make sure that you understand it because it will be important for us as we move forward in later conversations. All right, let's start off this conversation by defining what a confidence interval actually is. And remember that a confidence interval is just one way that we can use sample data to estimate a population parameter. The second way is through hypothesis testing, which is what we're going to cover in Chapter 8 in the next video. But for now, a confidence interval allows us to estimate a range for a true population mean or a proportion. So for example, if we were a meteorologist and we wanted to use a confidence interval to estimate the chances of a tornado hitting a certain geographical region, we could express that within a range of percentages. So even though we will be primarily using confidence intervals to express proportions and means, remember from Chapter 1 the relationship between proportions and percentages. It's really easy for us to convert from a proportion to a percentage simply by multiplying the value by 100, and it's a lot easier for us to understand and be able to communicate percentages, so just recall that relationship as we're moving throughout the duration of this lecture. When calculating a confidence interval, what we're essentially doing is estimating a best guess of where our true population parameter, whether that's a mean or a proportion, lies. We then develop an interval for which we believe that population parameter lies within a certain level of confidence. And there's 4 central steps that we do to calculate this. The first is to calculate the standard error. There's 2 different ways we're going to do that depending on whether or not it is a population mean or proportion, but that's always going to be the first step regardless. The second is to choose our level of confidence, whether that is a 90%, a 95%, or a 99% level. We then calculate the confidence interval itself, and then one last thing we're going to be focusing on is interpreting the results within the context of the problem. And so once we actually do our calculations, what does this mean respective to the research question that we are initially asked? So as I had alluded to, the first step of calculating a confidence interval is to calculate the standard error. And this is the way we would do that if we're dealing with means. So again, there's a different way to do this for proportions, but the way that we do that for a mean is to divide our standard deviation by the square root of the number of samples. So that's where this formula is coming from here on the right-hand side. All of these notations should look pretty familiar to us in terms of our S representing our standard deviation and the number of samples representing our population, so our capital N here. And for means, we use our estimate for standard error when our N exceeds a value of 50. And so just keep that in mind as well. So it's a slightly different look here in terms of calculating the standard error for proportions. Reason being is that we will be using our sample proportion value, which is designated by our lowercase p here on the right, as our primary mechanism for calculating our standard error. And so the way we do that is taking our sample proportion p and multiplying that by a value of 1 subtracted by that same sample proportion divided by n, which is the number of samples, and then we take the square root of that. The second step to determining a confidence interval is to choose the confidence level and the corresponding z-value. And so a confidence level is the probability that our confidence interval contains the true population parameter. And so these 3 confidence levels here are the primary ones that we will be discussing in this course, and what are also used primarily in terms of communicating social statistic information. So whether we want to be 90% confident, 99% confident, or 95. I would say in social science, the most common one that I've seen used is this 95% confidence level. It's also the one you'll see me use mostly in our examples in this lecture and also your problem sets and even exams, because again, I want to emulate what it would actually look like if you were to conduct this research yourself. And again, we use this confidence interval to determine the range that it will contain the true mean or proportion. So again, we're doing this step regardless of which one we're using. What we're looking at here on the right-hand side is a graphic that shows us those corresponding z-values. So remember from our conversation about determining z-values in our previous lecture, that the z-value shows us how many standard deviations we are away from our mean value. So that's what we have with x here in the middle. For a 90% confidence level, the corresponding z-value is 1.65. And you can take a look at this for yourself on the table as well. For a 95% confidence level, the corresponding z-value is 1.96. And lastly, for a 99% confidence level, the corresponding z-value is 2.58. And it's the same thing if we go the negative direction as well. Same value, just the negative. So negative 1.65, negative 1.96, and lastly, negative 2.58. So that's essentially establishing our boundaries here for what's considered our best estimate, or our confidence level in this case. To summarize our conversation about confidence levels and their corresponding z-values, I want to take a brief moment to talk about this chart. So what should look familiar to us are these confidence levels, as we just discussed in our second step, and what their corresponding z-values are on our standard normal table. I've summarized them for you here simply so you don't have to look them up every time you want to use them. These 3 levels, the 90, 95, and 99% confidence level values, are the only ones I will ask you about in this course. And so that's why I've summarized them here, because you won't have to look up any other ones otherwise. The new term that you see here, though, and what I want to talk about here for a moment, is this idea of alpha values. Alpha values are simply another way to express what confidence level we want to use. I'll illustrate this point in just a moment, so I won't spend too much time on it here. But what an alpha value does is correspond to the proportion value of the confidence level. So again, a 90% confidence level can be expressed as a proportion value of 0.9, and the alpha value is essentially telling us what the danger zone of our confidence level is. And again, we'll get to that in just a second. The corresponding alpha value for a 95% confidence level is 0.05, and lastly, for 99%, it's 0.01. Again, simply what I want you to understand here is the relationship between their proportion values. So a proportion value with a 95% confidence level is 0.95, so that extra 0.05 is what our alpha value corresponds to. And so let's say I asked you a question and I'm asking you to determine what the confidence level is for a population mean using an alpha value of 0.05. What that should trigger for you in your head is that we will be using a confidence level of 95%. So that's the only thing I really want you to take away from this slide, is what this relationship between these two terms are with alpha values and confidence levels. Again, they complement each other in that they add up to a total value of 1. So we can see that here with our 90% confidence level, proportion value of 0.9. If I add that to 0.1, I get a total of 1. Again, what we're doing here is just another way to indicate what confidence level we will be using. So again, one more time for an example. If I said, I want you to solve for the confidence level of a population proportion using an alpha value of 0.01, that should trigger in your head that I should be using a confidence level of 99%. And there, that Z value corresponding would be 2.58. So use this chart as a reference. I would add it to your notes because again, you're going to be using it not only for this chapter, but throughout the duration of this semester. And so just make sure that this is really locked down and that you understand the relationship between these three ideas. So again, the confidence level, a corresponding alpha value, and a Z value. So on the last slide, I alluded to this idea of a danger zone. And what I was trying to get at there was this idea of only being so certain or so confident when we're producing an interval. We can never be 100% confident that our true population parameter is going to lie within the confidence interval that we can produce. But we can try and increase our probability by being either 90, 95, or 99% confident. But let's take a moment here to discuss this idea of the danger zone and what I mean by that. The danger zone is this shaded region on either end of the extreme of our distribution, so both on the negative end and the positive end. So what we're looking at here is our sampling distribution using a 95% confidence level. And recall that overall, the area under a standard normal curve has to equal a value of 1. So whenever we're going to add together these proportion values on the bottom, just know that the sum total of the entire area has to equal 1 or something went awry. So in this case, let's break this down step by step. Essentially, our cutoff points to our danger zone values are going to be our Z values here. So from our standard normal table, what I just showed you on that last slide as well. For a 95% confidence level, that corresponds with a Z value of 1.96, and we see that both in terms of its negative value here on the left end of our distribution and a positive 1.96 on the right hand of our distribution. Our safety zone is what's here in white, which means, yes, our population parameter is going to fall within our interval, and there's a 95% chance that it will. But again, since we can never be 100% confident, there's a 2.5% chance that it's lower than whatever our interval is, and a 2.5% chance that it's above our interval. And the way I calculated that is, again, this idea of knowing that under the curve, it has to equal that value of 1. So a 95% confidence level corresponds with a proportion value of 0.95, which means I have an extra 0.05 left over. And knowing that I need to have a danger zone on both ends of my distribution to account for both the negative end and the positive end, I'm going to take the excess 0.05 from it. So again, just taking 1 and subtracting that by 0.95 to get 0.05 and dividing that by 2. Again, just so I can make sure I have two ends here. So that's where I'm getting the value of 0.025, or corresponding to a percentage value of 2.5%. Let's take another look here using a sampling distribution with a 90% confidence level. So a couple things to note here that have changed from the previous slide. The primary thing is that our safety zone has decreased in size because now we're only 90% confident rather than 95% confident. And as a consequence of that, our danger zones have increased. And so whereas in a 95% confidence level, we only had a danger zone of 0.025 here on both our upper and lower bounds, now that's doubled. Reason being is that at a 90% confidence level, our corresponding proportion value of 0.9 allows us to have that excess value of 0.1 total. Again, the entire area under the curve has to equal 1. So if I take 1 and subtract that by 0.9, I have 0.1 left over. And if I need an upper and lower danger zone, I know that I have to divide it by 2. So that's where we get our new danger zone category here of 0.05. Other thing of note is that our corresponding Z value has also changed. And so whereas a 95% confidence level ended in a Z score of 1.96, both on the lower and upper bounds, now we're dealing with a Z score of 1.65. And I took that directly off of the chart that we just noted a few slides ago. So now that we've made it to step 3, we can actually go ahead and calculate our confidence intervals. The formula is going to look slightly different depending if we're using means or proportions, but let's start off discussing our confidence intervals for means. The first thing that we'll have to do is determine what our best guess of the population mean is. And this will be information provided to you within the context of a problem, so don't worry about that too much for now. The second step is to determine the Z-score associated with our level of confidence. And so, for example, if I asked you to use a 95% confidence level, you would know that the corresponding Z value is 1.96. And I got that directly off the chart I used a few slides ago. You can also think of it if I asked you to use an alpha level of 0.05, that the corresponding Z value would also be 1.96. So essentially, recall that an alpha value and that confidence level are interchangeable terms. They're both asking you to use that same corresponding Z value, so make sure to reference back that chart. And lastly, we will be taking our corresponding confidence Z value and multiplying that by the standard error of the mean, which is what we calculated in step 1. In order to calculate the confidence interval for proportions, we're essentially going to do the same steps we just did for means with one exception, and that's with this sampled proportion, or P, listed here right on the front. So simply we're using proportions instead of means. We're still going to both add and subtract by our corresponding Z value with our confidence level, multiplied by our standard error, which again is what we calculated in step 1. The final step of creating a confidence interval is to interpret your results within the context of the problem. So in this case, what I've done here is essentially created a shell for you in order to interpret any type of result, whether it's for means or proportions. So in this case, let's go over our example for means. We would say we are blank % confident that the true population mean is between blank and blank. So for example, we could say we are 95% confident, or if the problem asks us to be 90% confident or 99, you would just fill that in this blank here, that the true population mean is between your lower bound of the value you calculate and your upper bound. For proportions, same exact idea. Let's say I asked you to be 90% confident. You would then say we are 90% confident that the true population proportion is between your lower bound value and your upper bound value. I think this will make a little bit more sense in the context of an example, so let's head there next. So the first example we're going to walk through is how to calculate a confidence interval for means. And this is a great example and opportunity for you to take a look at what a practice problem for either homework or an exam might look like. So let's pay attention to the format here. First thing, let's say we're interested in estimating the mean or average number of days someone is in pretrial detention. So how many days are they in a local jail between when they are initially arrested and when they're released? We're drawing a sample in this case of 67 individuals and find that on average, they spent 8.9 days in pretrial detention with a sample standard deviation of 1.2 days. So a couple of things to note right away. I have my N value here of 67. I have my mean value of 8.9 days and a sample standard deviation of 1.2 days. Now here comes the question component. What are we trying to solve for? In this case, what is the 95% confidence interval for the population mean or average time that people spend pretrial detained? So recall, our 4 steps to calculating a confidence interval include these. First, we have to calculate the standard error. Second, we have to determine the confidence level. Third, we have to actually calculate the confidence interval itself. And lastly, we're going to want to make sure that we interpret the results within the context of the problem. So revisiting our idea here of our local jail example, here I've pulled out the main information that we're going to need statistically to solve this problem. So again, our N value of 67 is our sample here. Our Y, or average number of days individuals spent pretrial detained, was 8.9, and our lowercase s, or our sample standard deviation, was 1.2 days. And lastly, I'm specifically asking in this problem you to use a 95% confidence level. So those are the 4 key pieces of information we'll need to solve this problem. So first step, calculating the standard error. In this case, for means, what we need to do is take our S value, which if you take a look at the last slide, we know was a sample standard deviation of 1.2 days, and divide that by our sample size. In this case, it was 67 individuals. I've done the math for us here. In this case, our standard error is 0.147. Our second step here is to choose the confidence level. Again, the problem specifically asked us in this case to use a 95% confidence level, so we know that the corresponding z-value is going to be 1.96. So now here in step 3, we can actually go ahead and calculate our confidence interval using all of the information we gathered from the question itself on the very first slide and our steps 1 and 2. So our Y bar, or the average number of days that our sample spent in pretrial detainment, was 8.9 days. Second, we determined that with the confidence level of 95%, the corresponding z-value is 1.96. And lastly, the standard error, which we calculated in our very first step, was 0.147. When I multiplied together our corresponding z-value and our standard error, I get a value here of 0.287. The last step I want to point out in terms of actually calculating the confidence interval is right here with our plus or minus symbol. Remember that we're creating an interval, or a range of values in which we believe the true population parameter lies. And because of that, we have to both add and subtract the value that we just calculated by multiplying our z-value and our standard error by our initial average amount. So in this case, I'm both adding the value of 0.287 to create my upper bound, and I'm subtracting that same value to create my lower bound. So whenever you see the result of a confidence interval, you should always have 2 numbers. The lower value should represent your lower bound, which in this case is 8.613, and our upper bound is the value of 9.187. Our final step here is to make sure that we are interpreting the results that we just calculated from step 3 in the context of the problem. Now that we have those 2 values, what does it actually mean in reference to the original research question that we had? In this case, using that same shell formula that we had from a couple slides ago, we can say that we are 95% confident that the true population mean, or average number of days in pretrial detention, is between 8.613 days and 9.187 days. What does this also mean, though, in reference to our standard normal curve? Remember, we can only be 95% confident in this case. So there is a possibility on either our lower or upper danger zones that the true population parameter isn't actually contained within this. So this bullet point here represents that chance. What this also means is that there is a 5% chance that the true population mean is outside of that range or fell into one of those danger shaded zones on our standard normal curve. So just keep that in mind. Again, our confidence interval is our best guess, but there is that small 5% probability that it could actually be outside of this range. Now let's go through an example of a confidence interval using sample proportions. And so a key way that I like to distinguish between determining whether I'm going to be using means or proportions is looking at the problem itself. In this case, what tips me off to knowing that we would be using a proportion in this case is this percentage sign right here. On the previous example, it told us right away that it was the mean or average number of days spent in pretrial incarceration. But here I know that there's an inherent relationship between percentages and proportions. And so I don't see any language within this problem about an average number or a mean number. So I know I'll be using my formula for confidence intervals in terms of population proportions. So let's take a look at this example here. A survey of a random sample of 78 incarcerated individuals report that 45% had been victimized in their lifetimes. What is a 90% confidence interval for the population proportion of incarcerated individuals who had been victimized? So similar to our example using confidence intervals for means, let's take a look at this question and pull out the relevant statistical information that we're going to need to calculate both our standard error and our ultimate confidence interval. Our n value in this case is 78, or how many people were in our sample. Our proportion value is 0.45, and the way that I get that is converting my percentage back into a proportion. So all I'm doing here is dividing our percentage value by 100. And lastly, I see that our question here is specifically asking us to use a confidence level value of 90%. In order to calculate the standard error, we need our initial p and n values. So our p or proportion value was 0.45. Again, I've gone ahead and done the math here, just plugging in numbers, and I get a ultimate standard error value of 0.056. We specifically were asked in this problem to use a confidence level of 90%, so I know that my corresponding z value is going to be 1.65. So in terms of calculating our overall confidence interval for proportions, remember that this formula just looks slightly different than that for means, where we're starting off with our p or proportion value instead of that average or mean value. So here I'm starting with my 45% victimization, or the proportion value of 0.45. Adding and subtracting that by my z value, again, corresponding to that 90% confidence level of 1.65 that we just got from step 2, and multiplying that by our standard error, which is what we calculated in step 1. Remember again that we're creating an interval or a range, so we're always going to have two numbers as our result here. What you do is take the result from multiplying your z value and your standard error and both subtract and add those in order to create your interval. In this case, our lower bound proportion value is 0.357 and our upper bound is 0.543. Similar to that same shell we just used to discuss our interpretation of our means, we're going to use the same thing here but for proportions. So in this case, we are 90% confident that the population proportion of people incarcerated who have been victimized is between 35.7 and 54.3%. One last step that you might have noticed here is that even though we created a population proportion interval on the last slide, I am interpreting this within percentages. Reason being is that if we were communicating this information to a non-criminological or non-statistical population, percentages are a lot easier for us to comprehend than proportions. So all you have to do in order to do this is multiply those proportion values by 100. So in the last interval, you saw that our lower bound was 0.357 and the upper bound was 0.543. I multiplied each of those values by 100 to get these percentages here. Last point here is now that we're using this 90% confidence level, we know that we have a 10% chance that the population proportion is not actually within our confidence interval. So, because we're less confident, our interval or our danger zones on the outer ends have expanded. So now we have a 5% chance on our upper bound that it's not there, and a 5% chance on our lower bound for that summation of 10% chance total that the population proportion is actually not within our confidence interval. Our safety zone has shrunk, so that means that our danger zone has increased. So just keep in mind that relationship between our confidence levels in both our safety zone and our danger zones change depending on how confident we want to be, and that's going to depend on what confidence level we ultimately end up choosing. All right, you have made it to the end of this lecture video, which covered our Chapter 7 material regarding confidence intervals. And I know this was probably a new concept for a lot of you again. So as a brief summary, remember that confidence intervals are simply one method in which we can use sample data to estimate population parameters. The second method that we'll be discussing, which covers hypothesis testing, will be in the next lecture video with Chapter 8. But for now, confidence intervals and a couple key takeaways here can be found right in the name. Confidence intervals simply mean we are giving our best guess, whether that's at a 90, 95, or 99% confidence level. There is a chance that our true population parameter, either being that mean or a proportion, can fall into the danger zone or outside of our safety zone where we think that interval range actually is. But it's not very likely, so that's where we can use statistics to not necessarily be 100% certain, but pretty confident. And we can do that by calculating it through 4 different steps. So again, these are going to be the same regardless of if you're using a mean or a proportion. In this case, your first thing is to calculate the standard error. There are 2 different formulas depending if you're using a proportion or mean, so make sure you understand the difference of knowing when to use each of those respectively. Second is choosing the confidence level. That will always be given to you within the context of the problem, so just make sure you have down that chart that we discussed in the middle of this lecture. So those corresponding confidence levels to the alpha levels and z values. Lastly, we calculated the confidence interval itself using the information that we gathered from the question itself in steps 1 and 2. And the very last thing is to interpret your results within the context of the problem. And I would argue this is probably the most important step. Reason being is steps 1 through 3 don't really mean much if we're not communicating this information properly. So make sure to take a look at both the examples that I have here and your problem sets to make sure that you understand how to go and take that interval that you calculate in step 3 and be able to interpret that within the context of the problem. That's something I will definitely be paying attention to when I am grading homework sets and exams. So if this is something that you think you're struggling with, either take a look back at step 4 or feel free to stop by my office hours or set up an appointment with me because again, step 4 is your key here. Steps 1 through 3 don't really matter without it. So with that being said, congrats on making it to the end of this lecture video and I will see you in the next one.